We are asked to sketch the solid given by an integral and then evaluate it. Our integral is from 0 to pi over 4 of the integral from 0 to 2 pi of the integral from 0 to the secant of phi times rho squared sine of phi d rho d theta d phi. Now remember, all of the stuff that looks like the integrand, rho squared sine phi d rho d theta d phi, all of that is simply dv. The solid is given completely by the limits of integration. As far as those limits go, we have phi going from 0 to pi over 4, theta going from 0 to 2, and rho going from 0 to the secant of phi. At this point, the hardest of these to deal with is rho. Let's look at it. We've got one boundary is rho is equal to the secant of phi. Well, I know that's the reciprocal of the cosine. If we multiply both sides by the cosine, then we have rho cosine of phi is equal to 1. And if we recall, rho cosine of phi is equal to z. So this is really z equals 1. It's a horizontal plane. Now that we have that out of the way, let's see how we're going to deal with phi and theta. And somehow here when I wrote this, I missed 2 pi. But theta going from 0 to 2 pi means we're sweeping all the way around the xy plane. And now let's deal with the phi. Phi goes from 0 to pi over 4. Let's get some axes. The upper boundary for phi is pi over 4. Now remember, phi is the angle made with the positive z-axis, which means now I'm considering an angle that's 45 degrees with the z-axis. And then because theta goes from 0 to 2 pi, I should sweep all the way around like that. Well, no, I can do better. I'll be right back. That's better. Now, to show that we're going to sweep all the way around, I'm going to give this a back edge. And now we have this angle here, which is pi over 4. And we're saying that phi sweeps from 0 to pi over 4. So we're interior to this, what looks like a cone. And then theta sweeping all the way around. And then we have this lid that is the plane z equals 1. And so this is our shape. It's a cone with a flat top. That's our sketch. Now let's compute the integral. I'm going to rewrite it. Looking at the integrand, we have a factor of rho squared and a factor of sine phi. So I'm wondering, maybe I can split this up into a product of integrals, but the upper limit for rho is the secant of phi. So I at least have to keep those two intact. I can, however, factor out the theta portion. So theta goes from 0 to 2 pi. It is the inner integral. It is the inner differential. So 0 to 2 pi d theta. Now for the rest of it, we have the integral from 0 to pi over 4. And now I'll go ahead and integrate with respect to rho. We have rho squared sine phi. But when I integrate with respect to rho, I'm using the power rule on rho. So this is 1/3 rho cubed. That's going to be evaluated as rho goes from 0 to the secant of phi. And then we have sine phi remaining d phi. Integrating with respect to theta gives me a factor of 2 pi, because that's from 0 to 2 pi. And then substituting for rho, the secant of phi, I'll pull out the 1/3, so we have 2 pi over 3 outside. We still have the integral from 0 to pi over 4, and it's going to look like the secant cubed of phi times the sine of phi d phi. But the secant cubed of phi, that means that there's a factor of cosine in a denominator. There are 3 of them. But if I combine a factor of cosine in a denominator with a sine in its own numerator, then what we really have is the tangent of phi times the secant squared of phi d phi. Letting u equal the tangent of phi, du is the secant squared of phi d phi. And so we can integrate the tangent using the power rule, 1/2 times the tangent squared of phi, but I have a 2 pi over 3 out front. So that gives me pi over 3 times the tangent squared of phi, evaluated from 0 to pi over 4. Since the tangent of pi over 4 is 1 and the tangent of 0 is 0, this results in an answer of pi over 3.